Welcome back, dear students. This is Tamás Jávor and Rubber Duck Physics. In the last video, we asked the question, if motion affects time, could it also affect space? We saw that a moving clock ticks slower, but does motion change how we measure distances and lengths as well? This leads us to another strange effect in relativity, length contraction. Length contraction means that objects moving relative to an observer appear shorter in the direction of motion. The word contraction means pulling together or becoming shorter. The faster the object moves, the more it contracts, just like time dilation became stronger at higher speeds. But just like with time dilation, the moving object itself doesn't feel any different. An object at rest in its own frame always measures its full length. It is only an outside observer, someone watching the object move, who sees its length contracted. Let's make this clearer with an example. Imagine a train moving at high speed along a track. The yellow duck is standing on the platform, watching the train pass. The blue duck is sitting inside the train. Now, from the yellow duck's point of view, the train appears shorter than it would if it were sitting still. But from the blue duck's perspective, inside the train, its length is completely normal. So, which length is correct? Both! Just like time dilation, length contraction is not about one correct answer. It depends on the observer's frame. Be careful, length contraction is not a mere illusion experienced by the observer. This is a common mistake students make when first learning relativity. If an object moves relative to an observer, its length is physically measured to be shorter in the observer's frame. Another mistake is thinking that the object is being squished by mechanical forces which somehow arise from very high-speed motion. This is not what happens. No new forces act on the object, it shrinks only because of the nature of space and time itself. Now, just like time dilation, length contraction follows a precise mathematical rule. The length contraction formula can actually be derived from the Lorentz transformations, just like time dilation. We won't go through the full derivation here, but it follows logically from the same principles. The formula for length contraction is contracted length equals proper length divided by gamma. Here, proper length is the length of the object measured in an initial reference frame in which it is at rest. And gamma, the Lorentz factor, is given by, as you already very well know, 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. As an object's speed increases, gamma increases, which means the contracted length gets smaller. This might still feel abstract, so let's see how it plays out in reality. Earlier, in video number 5, we mentioned muons in the upper atmosphere, but we didn't fully explain how they reach Earth's surface. We know the expected lifetime of these unstable particles, and even if right after their creation up there they head down to Earth on the shortest possible path, almost all of them should decay long before reaching the ground. But they don't. We detect many of them at the surface. Let's explain why. From Earth's perspective, muons are moving at nearly the speed of light. Because of time dilation, the muons' internal clocks, which is of course just a metaphor, tick slower than normal. This means they live longer and have enough time to reach the surface. But from the muon's perspective, something entirely different is happening. In its own frame, the muon is at rest, and it is Earth that is rushing toward it, upwards. So what explains its survival in this case? From the muon's point of view, the entire atmosphere is length contracted. The distance from where it is created to the surface of Earth is much shorter than it would be in Earth's frame. So, from the muon's perspective, It doesn't need extra time. It simply has a shorter journey to travel. Two perspectives, same outcome. Both time dilation and length contraction are explanations of why muons survive long enough to reach Earth. A similar effect happens in GPS satellites, whose software must adjust calculations for both time dilation and length contraction to provide accurate positioning to your device. Since these satellites orbit at high speeds relative to Earth, their onboard clocks tick slower due to time dilation. At the same time, from the satellite's perspective, the distance the signals have to travel from and to the navigational device on ground appears slightly length contracted. Without accounting for these relativistic effects in the calculations made to determine position on the ground, GPS positioning would be off by several kilometers per day. These effects are real, measurable, and essential for modern technology. At first, time dilation explained in the last video and length contraction from this video might seem like separate ideas, but they both come from the same Lorentz transformations and they always occur together. A moving clock ticks slower and a moving object appears shorter. These are just two sides of the same principle. But this raises an even deeper question. We have now seen that motion affects both time and length. But if two observers moving relative to each other don't agree on distances or time intervals, what does that mean for the order of events? Could two people moving relative to each other disagree about whether two events happened at the same time? That's what we'll explore in the next video. Before we go, if you would like one-on-one tutoring in IB/DP physics, A-level physics or mathematics, or AP physics, I also provide online lessons. If you would like extra help with relativity or any other topic, feel free to reach out. You can find my email address if you click on the channel information of the Rubber Duck Physics YouTube channel. It's only visible if you view it on a computer browser, not in the app. I'm looking forward to hearing from you. Thank you for watching Rubber Duck Physics. See you next time.